Hello everybody, my name is Dr. Stephen Wilkins and I'm here to talk to you about some of my own research. But before I do that, I just want to introduce myself. So I'm currently a senior lecturer down at the University of Sussex, so I do a mix of teaching and research. I was actually born in Yorkshire, over here just in Leeds, before moving to the University of Durham where I did my undergraduate degree. After that I moved down to Cambridge for a few years where I did my PhD in astronomy, and after that I moved across to Oxford where I worked as a full-time researcher. Now 6 years ago I got my lectureship in Sussex and so I moved down there. My work concentrates on a particular period of the university's history called the Dark Ages, and that's what I'm going to tell you about today. Now when I talk about the Dark Ages, I'm not talking about the medieval Dark Ages, kind of shown by this image over here from a very popular film. I'm really talking about a period of the universe's history when the universe was literally dark. Okay. So a little bit of context first. We've known since the mid-20th century that our universe is expanding. Okay? A consequence of this is that the universe in the past was smaller and therefore hotter and denser than it is today. Another consequence is that the universe has actually only been around for a certain amount of time. Today we think that is around about 14 billion years or so. Okay. Now, we're actually able to observationally probe the evolution or the history of the universe because of a property of light in that it has a finite speed. So as I look at you in the audience, I'm actually seeing you not as you appear instantaneously, but as you appeared a fraction of a second ago. Okay? As I look out into the universe, for example, looking at a galaxy like this, I'm actually seeing that galaxy as it really appeared hundreds of millions and sometimes billions of years ago, depending on the galaxy. Okay? So this property allows us to look out into the universe and actually watch the universe evolving over time. Okay. So one of the first key events in our universe's history was the process of baryogenesis. Now this is a process which actually created the normal matter that we have around us today, so the atoms that our bodies are made up of, or at least some fraction of them. So this baryogenesis, it left the universe composed of matter as opposed to antimatter, in addition to other subatomic particles and radiation. Now a few minutes after the Big Bang, some of this matter underwent nuclear fusion and went to form the light elements. So over here we created around 25% of the universe in helium, and around 75% of the normal matter in the universe found its way into hydrogen. And that's all there really was, apart from a little trace amount of even heavier elements. Okay. So that's not really what the universe around us, or at least even this room, looks like today. Now, as the universe continued to expand, it cooled, and eventually neutral atoms, as opposed to ionized particles, were able to form. Now, when this happened, light no longer interacted with the matter in the same way, and actually light could travel mostly freely through the universe. Now, today, we actually see these photons as what we call the cosmic background radiation, or the cosmic microwave background. This is essentially a snapshot of when the universe was only a few 100,000 years old, and this is what it looks like. So this is one of the most recent versions of this image, of this snapshot of the universe, taken by the Planck satellite only a few years ago. Okay. What you're actually seeing in this image is the distribution of matter in the very early universe. So what we can see from this is that some areas of the universe are more dense, colour-coded in red here, than other areas of the universe which are less dense. And it's over time, these areas of high density actually attracted more material to them, and they were able to form galaxies. Now, as the universe continued to expand, these background photons cooled. They were essentially shifted out of the visible regime and into the infrared and then the microwave. Now, what happened then is that the universe entered what we call the cosmological dark ages because the universe was literally dark. Okay, so if there was an observer around at that point, they wouldn't see any sources of visible light. Okay, but that doesn't mean that nothing was going on. In fact, during this time, these inhomogeneities, these little bits of the universe which were more dense than other areas, they continued to grow and accrete material. And so we actually saw structures forming. Okay, so this is a little simulation where what you're actually seeing is that over time, dark matter particles are accreting together to make these structures. And if you watch it long enough, you start to see these big blobs of matter coming together here. Now eventually stars and also supermassive black holes are able to form in these structures, and they begin the process of lighting up the universe. And so this is really now the epoch of first light, okay, when we first start seeing these stars. Now, these stars are typically very massive, and very massive stars are very hot, and they produce lots of radiation which is able to ionize hydrogen and other elements. Okay, so they produce photons which are able to break apart protons and electrons and leave them ionized. So these stars are actually able to return the universe back into the state it was before recombination. Okay, so this is a process called reionization, and we know that it happened kind of slowly over the first few 100 million years of the universe's history. Okay, so the toy diagram we have of this is that we form these first luminous objects. Okay, they're surrounded by neutral hydrogen, and over time they emit all these ionizing photons and they produce these bubbles of ionized gas. Now, if we wait long enough, we entirely reionize the universe. Okay. I should say, however, that there are some more exotic explanations for this process. We know this process occurred, okay, but we're not entirely sure of what actually did it. The best bet is on stars and maybe supermassive black holes, but it could be something more interesting. Okay. Now, many of these stars that formed in these very first galaxies, they exploded as supernovae. Okay, so very massive stars, towards the end of their lives, they essentially collapse, and as they do, they explode. Okay, and as this happens, these supernovae actually enrich their surroundings with heavy elements. Okay, so the stars are powered by nuclear fusion. And in nuclear fusion, you're taking light elements and making heavy elements. Okay? And so these stars enrich the surrounding universe with heavy elements. So things like carbon, nitrogen, oxygen, and even iron, and even heavy elements. Okay? So the gas enriched by these heavy elements goes on to form a new generation of stars, but also rocky planets like the Earth and even life. Okay? We're mostly made up of heavy elements that we created in these supernova explosions. Okay? This is just a nice actual image of one of these explosions or its aftermath. So you can see this material left off over here. So this is a long period of the universe's history, encompassing around 1 billion years, or around about 10% of the universe's history. Now personally, I like to kind of christen this period of the universe's history the First Light and Reionisation Epoch, and that's because it's got a good acronym, which is the FLARE. And anybody who's seen astronomy talks before, you'll be aware that we're full of acronyms all the time. We have things like the Very Large Telescope and the Extremely Large Telescope. Okay. In terms of my specific work, I seek to understand the FLARE through the combination of simulations and observations. Okay, so I'm trying to do both things here. I'm trying to observe the universe, and then I'm trying to simulate or model the universe to see if I can understand what's going on. Okay. So, observations of the FLARE. To understand galaxies, what we need to do is collect observations from across the electromagnetic spectrum. Okay. So this is a little bit of a technical diagram, but bear with me. So here what I have is the spectrum of a galaxy, just a typical galaxy which is maybe forming stars. And what I mean by spectrum here is how the luminosity of an object depends on its wavelength. Okay. So we can see over here, this is the rest frame wavelength, and so the visible light is this little bit in the middle, okay, and the UV and the near infrared on the either side, and then we have the far infrared over here. Okay. And if we want to learn about galaxies, we actually need to probe this entire spectrum. Okay. I'll show you why. First of all, if we just look in the ultraviolet, okay, this is light which is high energy compared to what we can see with our own eyes. Okay? And in an astrophysical context, this light is dominated by hot stars and active galactic nuclei. So those are objects which are fed by material falling onto a supermassive black hole. Okay? And they're really telling you about how much recent star formation there's been, how much AGN activity there is. Okay? We also see this really sharp break over here caused by the absorption of ionizing photons. Okay? This is actually really useful for astronomers because it allows us to work out how far away some of these galaxies are. Okay? So this is what we get with the ultraviolet. As we look into the optical or the visible, we're now seeing emission really produced by longer-lived stars, so including stars like the Sun. And this really tells you about how many stars there are in any one object. We also see there are all these strong emission lines, okay, these strong spectral features over here. And this is actually seeing gas which has been illuminated by stars. Okay. Now this is really important for astronomers because looking at these lines we can actually work out what that gas contains. Okay. As we move into the infrared now, what we're really seeing is starlight and light from AGN which is being reprocessed by dust and re-emitted. Okay. And so only only by looking across the full spectrum do we get the full picture of what's going on in galaxies. So specifically about the flare, well, observations of galaxies in the flare lie at the frontier of our capabilities. And that's because they're often intrinsically faint. We're looking at galaxies which are only just formed. Okay? They haven't had time to build huge numbers of stars. Okay? They're also very far away. The only way we're seeing something in the early universe is by looking very far away and exploiting the fact that light takes a long time to travel over that distance. Now, being very far away means they're also going to be very faint. And in addition, because of the expansion of the universe, their light is shifted into the infrared. Now, that's a problem because our technology isn't as good in the infrared as it is in the visible. Okay, so there's a technological issue there as well. And there's also an issue of the atmosphere, because we know our atmosphere blocks a lot of the infrared light. Now, for this reason, observations of the flare have really been dominated by our best, our state-of-the-art facilities. So this is just a little diagram showing kind of rough wavelength that each of these telescopes is probing, and then when they were first constructed, okay, and then the size of these circles gives you an indication of how big the telescope is. So we have things that I'm sure you've heard about, like Hubble, and maybe the Very Large Telescope. These ones on the ground, Hubble is in space. Then there are things like the Spitzer Space Telescope and the Herschel Space Telescope. Okay? Then over here, this relatively new one called ALMA. This is really an infrared or millimeter telescope. Okay? But in terms of actually observing galaxies in the flare, at the moment, we're mostly limited to what we've learned from Hubble. All of these other telescopes have observed galaxies in the flare, but really our knowledge of the flare has really been driven by Hubble. Okay? So Hubble is now almost 30 years old, but one of the great things about Hubble is it's in space, so it's above the atmosphere, which gives you a much less background, so allows you to be much more sensitive, but also it's still close enough that we can just about go and upgrade it. And in fact, the last upgrade to Hubble was now almost 10 years ago when what we call Wide Field Camera 3 was installed. And when that happened, we were really almost overnight able to find hundreds of thousands of new galaxies in this period of the universe's history, whereas before that we'd been limited to a handful. Okay. So this is what happened when Hubble was last upgraded. Okay, so you can just about see Hubble in the background over here. Okay, and what's actually seeing here is you're seeing multiple reflections. So we've got an astronaut's faceplate over here, another astronaut is taking a picture of them, and in the reflection you're seeing Hubble in the background. And this is when they were actually installing Wide Field Camera 3 in 2009. Okay. So since the installation of Wide Field Camera 3, we've been able to identify more than 1,000 galaxies present in the flare. And we've also constrained some of their really important physical properties. So we've been able to work out how much they contribute towards reionisation. Okay? And we've also been able to find that these galaxies contain dust. We've been able to say lots more about them. Okay? Possibly one of the most useful observations that we've taken is this over here. So this is the Hubble Extreme Deep Field or Ultra Deep Field. And this is one tiny fraction of the sky. So in fact, to get an idea of how small a fraction of the sky this is essentially 2 millimeters square, about this, held at arm's length from the sky. Okay, so a really, really tiny fraction. And this patch of the sky was initially chosen because it was known to be pretty empty. There was nothing bright in there. But when we observed it with Hubble for a large period of time, you see that it's actually full of thousands of sources. Okay? And in fact, the vast majority of these objects are all galaxies. Okay? There's only a handful of stars in this image. Okay? So a handful of relatively nearby things. Just concentrating on this little object over here. Okay? This thing here is a galaxy that we're seeing when the universe was less than 1 billion years old. And in fact, this is actually one of the best images that we have at the moment of one of these galaxies in the flare. Okay, so this galaxy over here doesn't look much like a galaxy, but it's really containing billions of stars. Okay, this is one of the best examples that we have. Okay, and this is forming perhaps its first generation of stars. Okay, there's lots of other galaxies like this in this image, okay, but this is actually the best one. Okay. Now the problem with Hubble though is that it actually doesn't probe very far into the infrared. Okay? So this actually limits our ability to study these galaxies. So in fact, Hubble is only really probing essentially this little tip of the UV. remember there's the redshift effect going on here. Okay, so we're taking the UV light and it's being redshifted, okay, into the infrared. And so what Hubble sees is just this tiny, tiny fraction over here. Okay, and so Hubble alone really doesn't provide us that much information. Okay, so we're missing out on any of the dust, and we're missing out on all these important emission lines and this kind of census of all the stars that are in here. Okay. Hubble also doesn't have any spectroscopic capability, or not very good spectroscopic capability. So even if we could see these emission lines, we couldn't really measure them in any particular detail. And also, Hubble is a relatively small mirror. Okay, so the size of Hubble's mirror is about the height of this room. Okay, so it's relatively small. Okay, and again, this is one of the best images that we have of galaxies in the flare. So you can imagine there's a lot more we can learn by looking in more detail. Now, luckily, the study of the flare is going to benefit enormously from a range of new facilities which are going to come online over the next decade. Okay? Many of these are actually designed specifically to explore the flare. I would say chief amongst these, though, is the Webb telescope. Okay? This is the upcoming successor to both Hubble and this other little telescope I mentioned, Spitzer. Okay? And it looks something like this. I always think this looks cool because it no longer looks like a telescope, it looks like some kind of alien spacecraft. What's really important for us, though, is that Webb is an international mission. In fact, it's a collaboration between NASA, the European Space Agency, which includes us, and also the Canadian Space Agency. Okay? And in addition, there are thousands, if not tens of thousands, of astronomers across the world who will be using Webb at some point. Okay? And Webb will be used to not just answer one particular question, it'll be able to answer a huge range of questions, all the way from observing the most distant galaxies in the universe, which I want to use it for, all the way to looking at objects in our own solar system and even examining the atmospheres of planets around other stars. Okay, so there's lots of science we can do with Webb here. So placing Webb on our diagram over here, it's due to be launched now in a little over 2 years, although it has been delayed a lot in the past, so that might change. But you can see it's kind of comparable size to the VLT, much bigger than Hubble now. Unlike Hubble, Webb is really designed to operate almost solely in the infrared. So whereas Hubble probes the UV, the visible, and a little bit of the infrared, Webb is really designed just to pick out this slice over here. Okay. Now, doing this actually influences many aspects of the design, but in particular what we're going to make the mirror out of, and also the thermal properties of the telescope. Okay. So because of the cosmological redshift, what this means is that Webb will actually be probing not only the UV emission of very distant galaxies, but also the optical emission as well, including all of these really interesting emission lines which allow us to tell us what these galaxies are actually made out of, so we can actually see the elements that are in the gas in these galaxies. Okay. So possibly the most striking feature of Webb is its mirror. Okay, and this is just one of the individual mirror segments over here. So you can see the size of these individual segments compared to the people. Okay, Webb has 18 of these segments in total. But probably the most striking feature is that these segments appear gold. And the reason why they appear gold is that they actually are coated in a thin layer of gold. Now the reason for this is that actually gold reflects infrared light a lot better than silver or aluminium. Okay? Silver and aluminium are very good for making visible light mirrors because they reflect visible light very well. Okay? But they don't reflect infrared light as well as gold does. And so the choice was made to actually coat Webb in gold. This is what the mirror looks like. Okay, so you can see all of the segments now attached. Again, you can see some of the engineers and technicians working on the telescope. And this was actually just prior to it going into the vacuum chamber here for testing. Now, by operating in the infrared, this actually adds some additional complications. When you're operating in the infrared, you actually want to make your telescope as cool as possible. Okay? And there's two ways in which Webb is able to achieve that. The first of these is via its sun shield. Okay, so this is what the sun shield looks like. It's this very, very thin reflective material. Okay, and Webb is always aligned so that the sun and the Earth, in fact, are always down here. And so the light from the sun and the Earth gets reflected off this sun shield. And so this allows the telescope, which would be over here, the instrumentation, to remain very, very cool. But also, unlike Hubble, Webb isn't in orbit around the Earth anymore, it's actually orbiting the Sun. And it orbits the Sun at a very special location in the solar system called the Earth-Sun second Lagrange point. Okay? So what this is essentially a position where we always have the Earth between the telescope and the Sun. Okay? So the telescope takes exactly a year to go around, okay? And it always has the Earth in between. So what this means is that the bottom of the telescope, where the sun shield is, can always be pointed at the hot things, the Earth and the Sun. Okay? So that makes cooling down the telescope a lot easier. This also actually makes controlling the telescope a lot easier, because then the telescope only has to move on one axis. Okay? A downside of this, though, is that the second Lagrange point is actually really quite far away. It's around 1.5 million kilometers away from the Earth, or around 5 times the Earth-Moon distance. Now, that's good because it allows the telescope to get very cool, but it's bad because it will make it almost impossible to ever go and fix the telescope if something goes wrong. Okay? And that is a big issue, but it's an issue that we have to overcome if we want to get the best out of this telescope. So the telescope will be launched on one of our largest launch vehicles. So this is the Ariane 5 rocket. So this is one of the European contributions to the mission. Okay? This is in fact one of the largest launch vehicles that we have at the moment. Okay. Now, in order to actually fit in this launch vehicle, Webb actually has to fold up. Okay? So what you're seeing here is the mirror. So this is the primary mirror over here, and the secondary mirror over here. This is all folded up to actually fit in the launcher itself. And so this is a little bit of a terrifying video, but what you're seeing here is the telescope actually unfolding. So this is after it's been launched, and this is while it's on its way to the second Lagrange point. Okay? The entire telescope has to unfold. Okay? So you can see there's multiple things going on over here. Okay? Now this isn't real time. This whole process is actually extending over around 11 days. So this is all done really, really slowly and carefully, okay, just to make sure there are no hiccups in this process. But nevertheless, although this has been tested, okay, I would say the astronomy community are still terrified that something will go wrong here. Okay. Now, in addition to my observational work, as I mentioned, I also work to simulate galaxies, and I thought I'd just kind of conclude on what that really entails, okay, because this is a big part of trying to understand the universe. So what I do when I simulate galaxies in the flare is I take some initial conditions, and it's really useful that these observations of the cosmic microwave background, they provide this snapshot of what the universe looked like when it was very young. So I take some initial conditions from there, okay, so how the matter is distributed, how much there is. And what I then do is combine that with our understanding of physics, essentially. So this includes things like gravity, hydrodynamics, which is how gas interacts, and then also the kind of messy baryonic physics, so things like how gas cools, star formation, the growth of supermassive black holes, and then things like supernova explosions. Okay? So we try and write equations which describe all of these things, and we combine these with these initial conditions and computer algorithms, and then combine this with a supercomputer. Okay? And when we do that, we're able to make something like this. So I showed this video right at the very beginning, but didn't mention what it was. This is essentially a simulation of a large patch of the universe, okay, not the entire universe, but a large patch of the universe. And what you're seeing here is galaxies growing, okay? So the orange kind of colours over here, this is the gas, which normally would be a little bit invisible, and the blue over here is the dark matter, which kind of provides a scaffolding. Okay, and so you're seeing time running forward now in addition to the whole thing rotating. And you see that material is falling into these galaxies. You see some really massive ones over here. Okay? And so as this material falls in, some of it gets turned into stars via star formation, some of it gets blown back out again when we have supernova explosions. Okay. So just as this video is running for the last few minutes, I just thought I'd come to my conclusions. And so I've tried to introduce very quickly today the first light and reionisation epoch, or the flare. Now this is a critical period of the universe's history, encompassing lots of major milestones. Okay? So for example, the reionisation of the universe, but also the enrichment of the universe with heavy elements. Okay? So the first enrichment of the universe with heavy elements, which go on today to form rocky terrestrial planets and life like ourselves. Now so far we've been able to get an idea of what's going on via Hubble and a few other facilities. Okay, so they've scratched the surface or provided the first glimpse of the flare. But really, to understand the flare, we're really waiting for upcoming facilities, and in particular, the Webb telescope. Now this will allow us to explore deep into the flare, to be able to find galaxies, but also dissect them and understand how they work. Okay. And so I'd just like to finish there and ask, are there any questions?